All right, so for today's lecture, I'm actually going to start kind of going over just with a little bit of examples, carry over from last time, and then we'll use that as kind of a starting point to hopefully kind of take a look at what other kinds of problems we'll be looking at with Chapter 7. Because I usually view kind of the end of Chapter 6 and most of the material that we cover out of Chapter 7 very similarly. They cover very similar topics, they're very closely related, and I often kind of just tie them and mesh them together a lot of times in covering them. And so that's kind of what I'm going to do a little bit here. From last time, as we were wrapping up kind of the end of Chapter 6, we were talking about electron configurations. So what I want to do is take a look at just kind of some example problems here. We want to take a look at giving the shorthand electron configuration for these atoms or ions, give the number of valence electrons that they have, and give the total number of unpaired electrons that they have, which kind of, I think, will incorporate some of those orbital filling diagrams that we had talked about in the previous lecture. So to do this, we'll just go through kind of one by one of these. We'll take a look at polonium first. So for polonium, if I get my iPad kind of ready here, if we take a look at polonium and we want to give its electron configuration, the first thing we're going to have to do is figure out where it is in the periodic table. And you do see like these Z equals and the numbers there. Hopefully it's kind of a refresher a little bit from earlier this semester when we talked about things like atomic number. That Z equals 84 means polonium's atomic number is 84. So if we're looking for it in the periodic table, we're going to find element number 84. Here it is. And so there's where polonium's at in the periodic table. Now, for the shorthand notation, right? We said for shorthand notation, we always start with the previous noble gas. So from polonium, previous noble gas is going to be xenon. And then for what comes after after the noble gas core to get to polonium, after xenon, we're down here. This is the 6th row of the periodic table. So this will be 6s. And then remember, as we jump down after the 6s, follow your atomic numbers, 56 down to 57 down here. Now we're jumping into the F block. So 6s first. And then to go to the F block, it's actually 2 less always than what our S and P count is. So 6s, 4F. And then as we get back to the D is always 1 less than what the S block is. So this is going to be 5D. And then we'll get 6P as far as kind of the shells. And the number of everything, we got 2 spots here in the 6s, so 6s2. Remember, the F block is really only 14 spots because one of these elements should be up here in this the way this periodic table is being shown. And I just wanted to use the same one as last time for kind of consistency's sake. But the F block is going to be 14, so 6s2, 4f14. The D block is 10 spots across. It is going to count the one of these that gets moved up here. So 5d10. And then for polonium, we're 4 spots in the P block, so 6p4. So as I write all of this out, we're going to have our xenon core. We said 6s2 because the 6s is full. And after 6s, we always jump down to 4f. And this will always be the order that we see for things then. So 6s2, 4f14. After the F, we go back to the D block, which is now only 1 less than whatever our S was. So now 5D, that's full. So 10, because it's 10 spots across. And then polonium was 4 spots into the P block, where it's going to be 6P. So 6P4. Right, so S and P always the same. D is 1 less. F is 2 less if we have them, because we won't always necessarily have these electrons for some of our configurations. All right, so this would be then our shorthand electron configuration. Now, the other pieces we were asked for the number of valence electrons and the number of unpaired electrons. So we can find the number of valence electrons from the electron configuration. It's basically everything that's kind of your outermost electrons. We can also get it, I think, easier by looking at the periodic table. So I'll show that first and then kind of relate that back to the configuration. And what we had said last time, if we're counting valence electrons, anything that's in the S block or the P block, we're basically just counting our columns, right? It's like 1, 2, we can skip the D block, and 3, 4, 5, 6. If we go down to polonium, that's where we would find it. So we'd expect 6 valence electrons for polonium. And if we're looking at the electron configuration, those 6 valence electrons are going to be the 2 in the 6s and the 4 in the 6p. So main group elements, which means like S block or P block elements, you expect basically their valence electrons to be all the S and P electrons. Because if it's in the S or P block for the element, your F and D shells will always either be empty or full. And so they're not really going to impact our valence electron count because of that. Like full D block shells don't count towards valence electrons counts for all of our main group elements. Likewise, if they were empty, it'd be kind of the same effect. We're mainly just looking at these outermost ones, which are going to be like the 6s2 and the 6p4. All right, so 6 valence electrons, that's what we said now. The last part of this is how many unpaired electrons are we going to have. And to find out how many unpaired electrons an atom or an ion is going to have, all you care about is the last set of orbitals that's not full, or any sets of orbitals that are not full. Like the vast majority of the time, unless you have one of those chromium or copper exceptions, the only sets of orbitals that aren't all the way full is going to be the last set of orbitals. So like in this case, like the S is full, the F is full, the D is full. So there won't be any unpaired electrons here because everything is full and paired. So all we care about is 6p4. And I think the one thing to be really careful of, just because 4 is an even number, that doesn't mean everything is paired. Right? So we want to think about what it means if we're in the p set of orbitals, there are 3 of them. Right, for our 6p orbital set. And if we have 4 electrons, if we follow Hund's rule, remember we fill them each one at a time first and then start pairing, which means there's actually 2 unpaired electrons in our polonium atom. So that's what we'd expect. That's kind of how we can go through and answer these. And if you want, this would be a good time to maybe pause the video and attempt kind of the next 2 examples on your own. And once you've attempted them, had a chance to kind of work through them, then you can kind of play back and see my explanations here that I'm about to give for both of them. And so I'm going to go ahead and start working through the example for nickel. So we're looking at nickel 2+ in particular that we want to get this information for. Well, periodic table, nickel's element 28, so we see it right here. So start with shorthand electron configuration would be an argon core, and then 4s2, 3d8 to the nickel. And so I'm going to write that first, and then we'll take into account the fact that this thing is an ion. So if it was just plain nickel, we would get an argon core, and then we would have, oops, that should be 4s2 and 3d8. But since this is nickel 2+, we're still going to have that argon core, but think about which 2 electrons come off first. We said last time the electrons that come off first are the one with the highest principal energy level. So in this case, 4 is bigger than 3, so these 2 4s electrons are going to be the ones that come off, and what we'll be left with is 3d8 for the electron configuration for that nickel 2+. Now, the next piece of this then, here is our electron configuration. Now we want to find our number of valence electrons. Well, if all of these are a noble gas core, our valence electrons are our outermost kind of not full energy levels. Well, 3d8, that's not a full energy level or not a full shell. And so all 8 of these are valence electrons. So nickel 2+ should have 8 valence electrons. Nickel on its own, if it was neutral, would actually have 10. Remember, you count S and D electrons for the valence electrons on a transition metal. Now, the last part of this, we have 3d8. We're trying to find out how many unpaired electrons this is going to have. So I'm going to slide this up a bit. So to count our unpaired electrons, we're going to want to think about our outermost orbital and how we're going to fill our d orbitals with 8 electrons. And so this is where we kind of have to know that from things we talked about before, there's 5 d orbitals in every energy level. So I would think of having 5 d orbitals that I'm going to put those 8 electrons into. And again, following Hund's rule, one at a time. That'll be 5. Now I start pairing. And what I notice is I still, kind of like my last example, I'm going to have 2 unpaired electrons at the end. Right? That's how we're finding that. So we're really looking, anytime you have to find like unpaired electrons for an atom, you're basically just mapping out that orbital filling diagram to see which electrons are left unpaired at the end of it. All right, last example of this type, then we'll kind of move on. So here we have arsenic 3+, another ion. So arsenic 3+, arsenic is element 33. Arsenic is right here on the periodic table. So previous noble gas, similar to the nickel, is argon. And to get to arsenic, then after argon, we're going to have 4s2, 3d all the way full should be 10, and then 4p3. And that would be normal arsenic. And then we'll look at, again, the ion side of things. So we have arsenic, normally would have an argon core. And we said it's going to be 4s2, 3d10, and then it should be 4p3, because there's 3 spots into that p block for arsenic. But now again, we want to think, what's going to happen if we take 3 electrons away? So arsenic 3+. Still going to have that argon core. And in terms of the electrons that come off, we always pull them from the highest energy level first. but we have 4s and 4p. And so if you have the same principal energy level, you're going to take it away at the one, or take the electrons away from what the highest L value orbital is, which is going to be the p orbitals before the s. So in this case, if it's arsenic plus 3, these are the 3 electrons that are going to come off, that 4p3. And so we'll be left with 4s2, 3d10. Now, in terms of valence electrons, right, arsenic itself is not a transition metal, and we notice this d shell is full, right? So these do not count for valence electrons. Arsenic 3 plus would actually just have these 2 electrons left to act as valence electrons. So in this case, we'd have 2 valence electrons for that ion. It would have been 5 valence electrons if it was just normal arsenic. And then the last part are unpaired electrons. Well, if we're arsenic 3 plus, where this is our electron configuration, we have 4s2, 3d10, everything should be full, which means it should all be paired. Right? And again, I can draw out those 3d orbitals similar to what I did for the previous example. And if I have 10 electrons, well, that just means that every single electron is paired, so that there's 0 unpaired electrons for that arsenic 3 plus. All right, so hopefully that's kind of a nice review over things that you saw last time. And like I said, these electron configurations, they are pretty important because there's something that really you're going to see them show up and be kind of relevant to a lot of the different trends that you're going to see that we're going to talk about here in Chapter 7. And so if you understand a lot with configurations, we're going to talk about some things here with periodic trends that hopefully those two can tie together some. And then those periodic trends are also going to be very applicable to things that we're going to see in the coming chapters as well. So for that, I think we're going to go and move back to kind of some lecture material. So we're going to take a look at talking about our Chapter 7 content, which is mainly focused on what we call these periodic trends. So what a periodic trend is, it's basically any physical or chemical property that follows a general pattern kind of across the periodic table, whether it's across a row or up and down columns. There's a general pattern across the periodic table. Now, that doesn't mean there can't be exceptions, because most of our trends do have exceptions, but the vast majority of the periodic table usually follows these trends. One that doesn't come up as often, and so I'm not going to spend as much time, I'm just going to give this as kind of a generic example, is something called metallic character, which really all metallic character is how metallic a particular element is. And if we think about periodic table, and I'll kind of zoom out again just to show the periodic table that I had a second ago. If we look at a periodic table, if we think about where our metals are, they're usually at the bottom of the periodic table or to the left, which means the bottom left of the periodic table is probably the most metallic element or elements, and the top right is the least metallic. So things like fluorine or helium, those are very much not metals in the way that they behave. And so that's kind of what periodic trends generally are going to look like. They have a general trend that as you move a direction like up or down a column or across a row, like you're going to see that property increase or decrease with a pretty consistent pattern. So what are the periodic trends that we are going to care about? Because like I said, metallic character probably isn't one you're going to see come up very much. It does have a general trend. As you move to the left in the periodic table, the elements become more metallic, and as you move down, they become more metallic, because that's where we find most of our metals in the periodic table. So when we look at these trends, I usually like to start with what I consider kind of the major trend that really kind of rules all of the other ones, because really this is the trend that is the explanation behind the trends we see for everything else we talk about usually in this chapter. And that's something called effective nuclear charge. You'll see it represented with Z with the lower, and then kind of like a subscripted like EFF for effective. What this effective nuclear charge is, it's the approximate charge from the nucleus that your outermost electrons are going to feel. And this is actually responsible for a vast majority of properties that most atoms have. And if you're looking for kind of like how do we calculate this, generally our effective nuclear charge, Z effective, is going to be equal to Z, which is really just our atomic number, minus what's called shielding effects. This is basically what happens when we have electrons that are closer to the nucleus that are effectively going to cancel out some of the positive charge from the nucleus that the outer electrons would feel. And I'm going to show some pictures with this that'll hopefully help kind of make sense of it. So these outermost electrons in an atom, and again, this kind of is almost like a Bohr model type picture, which isn't perfect, but in this case, it gives us enough of a visual image of kind of what's going on, I think, to kind of understand what happens. But our outermost electrons, these are going to be the electrons in the highest energy levels. These electrons aren't going to feel the full positive charge of the nucleus because there's some electrons that are already closer, and those electrons that are closer are going to cause repulsions to those outer electrons, which effectively cancels out some of the attraction from the nucleus. And so our effective nuclear charge is how much pull do these outer electrons feel from the nucleus with the repulsions kind of factored into that. And it sounds like it's something that's really complicated to calculate, and if we're trying to be really, really precise and accurate, it kind of is, although we can kind of generically estimate it fairly well with some simple means. But one of the ways you'll typically see this kind of approximated is by taking whatever the charge of your nucleus is minus what we call all of our core electrons. And that's why we define the kind of like core versus valence electrons in our previous lecture material. All right, so some other general things dealing with effective nuclear charge. Orbital type also matters. So the orbital type has a lot to do with kind of how far from the nucleus, as well as kind of in the shapes, probably more to do with the shape, obviously, of the orbitals. But it turns out that those shapes play a huge role in kind of the overall attraction to a nucleus. Right? We saw kind of s orbitals that are in the same energy level as a p or a d or an f orbital. S is always the lowest energy, then p is the next lowest, then d is above that, and f is always the highest energy orbital within a principal energy level. And so we see effective nuclear charge follows that similar trend. Like the higher an energy an orbital is, the lower the effective nuclear charge, because those electrons aren't held as tightly. That's why they're kind of in a higher energy orbital. Although it is slightly more complicated than that, but that's kind of a general way to kind of approximate and think about them, I think, at least, especially initially, when you're trying to approximate general effective nuclear charge of things. So if everything has the same principal quantum number, the L value is kind of the next thing that matters. The bigger your L value, which is kind of the order you see here for these orbitals, the bigger the L value, the higher energy the orbital, but the weaker the effective nuclear charge as a result. Now, the trend that we actually see in the periodic table for this particular property, this is what we call effective nuclear charge. It's not one that's immediately obvious, at least I think. Like the up and down trend, I think, is relatively obvious to me anyway. I have some kind of some kind of thought about it, and that's overall we're going to see effective nuclear charge increase up to the right. And I'm going to look at kind of both effects as far as going across as well as up and down, and kind of some big things to think about as far as where this trend comes from. I'm going to show some very specific examples to hopefully help everyone understand why this is the trend. And what's going to happen here is as you go up to the right in the periodic table, your outermost electrons, the more electrons you put in your outermost shell, your outermost ones, since they're all so far away, they don't really shield each other very much because they're all kind of somewhat similar distances from the nucleus. None of them are so much closer. They're really blocking out the other ones that are in that same energy level, at least not all that effectively. And so as you go to the right on the periodic table, you basically add an entire proton, which the nucleus charge goes up by a full 1, but that shielding effect does not go up by a full 1. It only goes up by a little tiny bit. And so the net result is the overall effective nuclear charge that's left is going to increase. So as examples, we would say things like fluorine has a higher effective nuclear charge than nitrogen. And if I show the periodic table, right, fluorine is farther to the right. It's more up to the right of the periodic table than nitrogen is. So fluorine has the higher effective nuclear charge is what we would say, or how we would describe that. Now, besides like a nitrogen-fluorine comparison, we can compare things that are in the same column, like fluorine and chlorine. Fluorine is directly above chlorine on the periodic table. And so again, if effective nuclear charge increases up to the right, if fluorine is directly above chlorine in the periodic table, fluorine's higher up, so it has the higher effective nuclear charge. And so all of our periodic trends have pretty distinct patterns like this. And really what we want to recognize is kind of what are those patterns. And when we get to our other types of properties that have these general trends, if we think about effective nuclear charge and what its trend is, this fact that it increases up to the right, we can use this to describe why our trends are what they are for pretty much all of our other properties. And that's part of why I'm spending a pretty good amount of time on this trend, maybe compared to what I will on the general trends for some of the others. Because really, this one trend is responsible for the trends we see in things like atomic size, ionization energy, electron affinity. I'll even introduce electronegativity a little bit at the end of the day as well, because it's also a periodic trend and also fits kind of in the same patterns that we see out of the rest of these. So to give kind of a good visual example with effective nuclear charge, just a little bit more detail on it, hopefully this image I think helps a lot trying to demonstrate it. So for magnesium, magnesium and chlorine, I'm going to first show just periodic table, kind of relate where these two are on the periodic table. Right, chlorine is right here in the third row, over on the kind of towards the far right. Magnesium's also in the third row, but towards the far left of the periodic table. And what we've said before is, as we go to the right on the periodic table, our effective nuclear charge gets higher. So that means chlorine's effective nuclear charge should be bigger than magnesium. So if we look at the slide and look at these images, the reason for that is if we think about these outermost electrons, the pull these outer electrons feel, that's our effective nuclear charge. The way we usually calculate that is by taking however many protons are at the center. And so we see here there's 17 protons on chlorine, there's only 12 on magnesium, and we subtract what we call the core electrons. Well, in these two images, the core electrons are the red ones. Those are the ones at lower energy levels. They're like the noble gas cores for pretty much all of our main group elements. And so chlorine and magnesium both have 10 core electrons, but because chlorine has 17 protons, all of these outer electrons, even though there's more of them, are going to feel an overall stronger pull from that nucleus. And so an effective nuclear charge approximation for chlorine, one of the very simplest approximation of this is not the most accurate way. There are more accurate ways to do this, but for us, we don't really need those really exact ways of doing this to understand our trends, which is what we really care about here. So kind of the simple method's really nice. We can just take 17 protons of the nucleus minus the 10 core electrons, approximate outer pull from those, or the approximate charge that those outer electrons get pulled with is about a +7 charge. For magnesium, there's only 12 protons, but it has the same 10 core electrons from the same neon noble gas core for the electron configuration. And now those outer 2 electrons magnesium has feel much less positive charge from the nucleus. They only feel about a +2 charge pulling on them, as opposed to the +7 in chlorine, because there's just so many fewer protons at the nucleus to basically pull on them. Now, visually, if you look at these two images here as well, you kind of get a preview as one of our next trends that we're going to move on to in a second, which is going to deal with atomic size. The bigger our pull on the outer electrons from the nucleus, the tighter those electrons are going to get pulled. Meaning that really, as we go to the right on the periodic table, our effective nuclear charge is increasing, but it actually means that the size of the atoms themselves is actually going to decrease, because the size of the atom depends on where are these outermost electrons. If they feel a stronger pull from the nucleus, they're going to get pulled tighter. And so you end up with smaller atoms actually as you go to the right. So here's a visual demonstration of that trend. We see here as we go across to the right on the periodic table, our radius actually gets smaller. And then as we go down the periodic table, our radius usually gets continuously bigger, particularly again for the main group elements. We won't do as much for comparisons on the D block. I will make a mention of them in a second because they are kind of the exception to the atomic size trend. And we will talk about why momentarily. But the big thing, if we look at this, we see a pretty big size change going from left to right. And these are for, again, just our pure, plain, neutral atoms. And again, going down. Going down, I think, makes just intuitive sense. Basically, each row you go down in the periodic table, you're adding an extra full layer of electrons kind of onto each atom. So it makes sense that they're getting bigger. As we go to the right, this is the part that I think doesn't always make sense, at least initially. As we go to the right in the periodic table, we're adding more protons and more electrons to our system. But because of the trend we just saw with effective nuclear charge, chlorine has, for instance, we said, a much higher effective nuclear charge than magnesium. That's why chlorine is much smaller than magnesium. Those outer electrons feel a tighter pull, so the atom actually gets pulled in and ends up smaller, even though there are more kind of building block particles of protons and electrons in the atom itself. Now, D block, I'll mention some things here just verbally first, and then we'll see it again kind of in the slides, I think, in a minute. We see most of the D block, especially as we get to kind of the middle of it and beyond, it doesn't change very much in size. And actually, as we go down, it doesn't even change that much in size, particularly the second, like literally what our second and third row of our transition metals don't really change much between each other. So there's a couple reasons for this. One, I'll explain the kind of side-to-side trend here. For transition metals, as you go from left to right, remember where you're adding your electrons. You're adding them to those 3D orbitals. But in terms of what determines an atom's size, it's the outermost electrons. But the outermost electrons of all of these transition metals is not the d orbitals that we're filling as we go across. It's those 4 s orbitals that actually filled before them. They're actually a little bit further away. And that's why, like the ions we saw at the very beginning earlier today, the ions lost the 4 electrons first. The reason for that really was they're the outermost electrons. But because those are the outermost electrons, as we add electrons to d orbitals, what happens is we add going from, for instance, manganese to iron here. We add 1 full proton, but the electron we add is actually at an inner energy level. It's not in the outermost possible one. And so because of that, we actually add a pretty high shielding effect too, which means the effective nuclear charge going across this d block doesn't really change very much. It actually stays pretty constant. And that's why the sizes, particularly from chromium on over, most of these sizes are about the same. There's not very much change. Now, going down the d block, it gets a little bit more complicated, like particularly between like the second and third row of transition metals. If you go on and want to take more chemistry or physics, particularly chemistry, we'll probably eventually get to talking about this. It's something called relativistic effects. Basically, your atoms get so big that your electrons start moving so fast that your orbital shapes start deforming a little bit from kind of the normal shapes we talk about. And it has some weird effects because of that. One of the effects is that your s orbitals like kind of shrink and get held a little bit tighter. And since your s orbitals are where your outermost electrons are, if they get shrunk and pulled in tighter for the really big atoms, that's why the sizes of what should be really big atoms aren't much bigger than the ones that are right above them, in the D block in particular. In the S block and the P block, that trend still mostly follows suit. As you go down, things get bigger. But like I said, transition metals kind of have weird trends. Going down, size gets a little bit bigger from the first to the second row, but from the second or third row of the transition metals, not much changes. As you go left to right, it decreases a little bit at the start, but then the size is pretty constant. And again, that's because just your effective nuclear charge doesn't change much. The down pattern is, again, I call it relativistic effects. Probably not something that's super important to general chemistry, but if it's something you're interested in, it's something we do see more like in upper level classes. I kind of throw in a pitch for myself here, I guess, because I teach inorganic chemistry where we do get to talk about some of that stuff that I think is actually pretty cool. All right, but anyway, moving on to things that we are going to have to know a lot more about this semester, application of these general trends. So atomic size, we said here already that the size of an atom really is dependent on its outermost electrons, and that our general trend is that size increases going down, because basically we're just adding a layer of electrons each time we go down. And then it also is going to increase as we go to the left, or you can think of it as decreasing as we go across to the right. Either way, whichever way is easier. I actually, a lot of times, will think of atomic size as increasing down and to the left. And the reason I think of that, it's the opposite of effective nuclear charge. Right? Effective nuclear charge increased going up and to the right. So atomic size is going to increase in the opposite directions. Because the stronger your effective nuclear charge, the tighter electrons get pulled, so the smaller things get. So if effective nuclear charge is getting bigger, atoms are getting smaller instead. And that's why we see this trend. All right. And this is, again, some visual trends for people to be able to see things. The blue line we see here is effective nuclear charge of our third row elements, starting at sodium and going kind of across the third row of the periodic table. The red line is the atomic radius of each of those elements. So as the effective nuclear charge goes up, we see a pretty consistent decrease in the size of our atoms. That's the major trend here that we're looking at. The exact numbers, don't worry about them. You do not need to memorize any numbers for any of this stuff. This is all about really just kind of conceptual comparisons to be able to apply these very general trends. Now, one of the things we can add on to atomic size and talk about that's somewhat similar is the size of ions. So we'll talk about this, and then we'll take a look at a couple examples of applying the trends to make some comparisons, and then we'll get into kind of our last couple of trends and do the same. So for ion size, there's not a really easy, fast trend in terms of like going up or down the periodic table. It actually has more to do with comparing the charges of the ions that you're looking at. That's going to be extremely important. It's very easy to compare the ionic radius of a particular ion to its original atomic radius. In general, cations are always going to get smaller than they started out, and anions will always get bigger than they started out. And if we want to think about what's kind of some of our reasoning behind that, for our cations, they're losing electrons. If you lose electrons, there's fewer electron repulsions. And if there's less electron repulsions, there's less overall shielding. That means a higher effective nuclear charge. Really just if there's less things pushing the electrons farther away, it's easier to pull them all in together. Whereas you get the opposite effect if you're adding extra electrons. That's a bunch of extra electron repulsions. That means those electrons have to spread out further from each other and further from the nucleus to try and stay away from each other. And so it causes ions to get bigger as you add more electrons and make anions out of things. Now, in terms of comparing size, when we're looking at ions in particular, usually they have to have something in common for us to be able to compare them. Like we can't choose any two random ions and expect to just immediately compare their sizes. It's a little bit more complicated because the starting atom sizes might have been very different. But if there are things in common, there are ways for us to make comparisons. So, for instance, any ions with the same atomic number or the same number of electrons can be compared. So we need one of those two things to basically be in common between the ions that we look at. Right? So if we have ions that have the same number of protons, these would basically be ions of the same element. Right? So you imagine if we compared like neutral oxygen to oxygen +1 or oxygen -1 or oxygen 2-, which is its most common ion, the trend that we're going to see is the more electrons we have, then the bigger the ion's going to get. Right? The fewer electrons we have, the smaller it's going to get, which should be in line with kind of the general things we just said. Right? Cations usually get smaller. It's not a usually. Cations always get smaller. Anions always get bigger. And then if we have two different ions that have the same number of electrons, there's actually a term that you'll sometimes see called isoelectronic, which represents like things that have the same number of electrons in them. And so what we can do is things that are what we call isoelectronic or have the same number of electrons, we can compare how many protons things have. Because if two different ions have the same number of electrons, whichever one has more protons is better going to pull those electrons closer and make a smaller ion. Whichever one has fewer protons, it can't pull things in as tightly, so it's going to be bigger as a result. That's kind of the general trend. Now, another way to think about both of these, and we'll see this with the examples that we see in a second, if you're looking to kind of simplify it as much as possible, the more negatively charged your ions are, usually the bigger they are. The more positively charged your ions are, the smaller they're going to be. That's probably the most generic trend that you can really see when comparing sizes of different ions. And so I'll show some visual images, and then we'll take a look at, like I said, just some general comparison questions. So to get an idea for just how much ion size can really change, here's a chart basically of the normal radius of a group 1 metal versus the radius of that metal once it's an ion, once it's lost an electron. And we see when things lose an electron, not only do they get smaller, they get a lot smaller. Right? Lithium goes from somewhere around 150 picometers for a radius for neutral lithium to somewhere down like just a little over 50 or closer to 60. So that's just a fraction. It's like less than half of its original size. And we see most of these, they're somewhere in that ballpark of almost like half their initial size. So losing an electron, like that can usually cause a really big change in the ionic radius, especially for those group 1 and 2 metals. Group 2 metals, these are now the +2 ions in particular that we're seeing, but we see all of them are, again, considerably smaller. Usually less than half of the original size. Barium maybe is a little bit more for its cation, but most of these are considerably smaller than they start out when we make those cations. The other side of that, anions get much bigger, right? So here we have the different nonmetals, fluorine, chlorine, bromine for some examples, that we add an electron to, and now these things get almost twice as big, kind of going in the other direction. So charge really, really matters to the size of things. And you can kind of get a feel for it here too, right? We think here neutral sodium is really, really big, approaching 200 picometers for radius. Neutral fluorine's down here way under 100. But if I make sodium plus, it's at about 100, and F minus is well above 100. So F minus is bigger than Na plus, even though sodium is much, much bigger than just neutral fluorine. And so we do see some big size changes in ions when we make those ions instead of just having the neutral atoms. So that's why we talk about these trends. So here's some general comparisons we'll take a look at, and then I have a couple other ones I'll add on that worksheet that I had a second ago. So first examples here, we're taking a look at magnesium versus calcium. We want to know for these different pairs, which atom or ion is bigger. So between magnesium and calcium, we want to know what's bigger. We think about our general atomic radius trends. Things get bigger as they go down and as they go to the left on the periodic table. Well, if I pull up a periodic table, I'll leave these examples kind of sitting over here. if I pull up our periodic table, oops, sorry, we're looking for magnesium and calcium. In this case, here is magnesium and calcium, right? Magnesium is higher than calcium on the periodic table. Calcium's farther down, so as a result, calcium should be bigger, right? In fact, if I put that here, I'll do that here for some of these explanations. Calcium is much bigger than magnesium, or at least it's noticeably bigger than magnesium because it's lower on the periodic table. Right? If we look at the next example, compares magnesium with sulfur. So here we have magnesium, here we have sulfur over here, it's in the same row. And we said the trend normally is things get bigger as we go down or to the left. Sulfur is much farther right on the periodic table than magnesium, so magnesium should be much bigger, right? Because as we go across to the right, our effective nuclear charge goes up, but in turn, because the effective nuclear charge goes up, the outer electrons get pulled in tighter, and so that means your size actually gets smaller in those cases. And so magnesium and sulfur, magnesium should be the bigger one. All right, the next comparison, and I'll go back to the slides here, because especially for this, actually I should just leave it up here, it might be easier, sorry. Between sulfur and sulfide, S2-, if we're comparing these two, if we go from a neutral atom to an anion, the trend is always the anion is going to be bigger. And kind of the general trend I said before, if you have charged particles, the more negatively charged something is, likely the bigger it is as a result. The more positively charged it is, usually the smaller it is as a result of that. Because if it's more negatively charged, we've added extra electrons, it's extra repulsion, so the sulfide, the S2- in this case, should be much bigger. All right, now, the last question of this, and this is again where it gets kind of interesting, we said before, neutral calcium is bigger than magnesium, magnesium is bigger than sulfur, and now we're comparing sulfide, S2- to calcium 2+. But what we're going to see is that, well, based on just atom sizes, calcium is much bigger than neutral sulfur, but the ions don't necessarily follow the same trend. So I'm going to go back to the periodic table for this one. If we compare sulfur 2-, so sulfur is right here, it's element 16. If it gains 2 electrons, electron configuration-wise, it's like argon. If calcium loses 2 electrons, it's element 20, it's also going to be like argon. So this is the example where the 2 ions we're looking at are what we call isoelectronic. They have the same number of total electrons. In that case, we said the one that has more protons is going to be better at pulling the electrons in, and it's going to be a smaller ion, right? Calcium has more protons. It's going to have a better, it's going to be better at pulling the electrons in tighter, so it's going to be a smaller ion as a result. Or, from a really generic sense, calcium is much more positively charged. Sulfur, the sulfide, the S2- here, it's much more negatively charged. Positive charges get smaller, negative charges get much bigger, so the sulfide is going to be the bigger ion of this pair. And so if you're able to compare ions, kind of a quick trick that helps make things a little bit easier, the more negatively charged it is, the bigger it's going to be usually out of that comparison. The more positively charged, the smaller. And it's almost like a ranking by charges. Like if we had something else in here like potassium +1, like if we had calcium 2+ and potassium +1, like the calcium 2+ is going to be smaller. Again, it has the bigger positive charge, we'd expect it to be smaller. If we go look at the periodic table, between calcium and potassium, calcium would have 1 extra proton. So from the trends we saw earlier, calcium 2+ would be smaller than the potassium 1+ because of that. All right. And so I think I'll come back to the worksheet as a wrap-up point. So I'll talk about our other trends here because there's not many more of them for us to talk about. And I think it'll be easier just to review all the trends at the end with a few wrap-up examples. So our last couple of properties that we're going to talk about, again, are kind of somewhat similar. The trends are going to follow similar patterns to what we've already seen. And so the next one we're going to take a look at is what we call ionization energy. So ionization energy, it's the energy it takes to remove basically your outermost electron while that atom's in the gas phase. And the gas phase part of this, it's not too relevant to us right at this exact moment, but it will be more important definition-wise when we get to something called the Born-Haber cycle a little bit later this semester. And so visually, basically what we're doing for ionization energy, we're just ripping the entire electron off the atom. And it's how much energy does it take to do that. And these are usually going to be pretty big energies, right? Because to take an electron all the way off an atom, it's not usually a very easy thing to do. Now, it will vary, obviously, from element to element, and that's why there's these trends in that we're going to talk about. So the general trend for ionization energy is that it's going to increase up and to the right, right? That's kind of I have decrease going down, but I think an easier way maybe to think of this is increases to the right, and also decreasing going down is the same as increasing going up. So I when I'm thinking about trends, will often kind of think about things as most trends, and we'll see this with the ones that are about to come as well. Most trends will be the exact same as effective nuclear charge. They're going to increase up and to the right. And the reason for that is really because of the effective nuclear charge. As the effective nuclear charge gets bigger, it's going to get harder to pull off an electron. So effective nuclear charge increases as we go to the right on the periodic table. So ionization energy is also going to increase as we go to the right on the periodic table. And then from a size perspective, we saw effective nuclear charge increases going up, or we can say it decreases going down. It's kind of the same idea. But as your atoms get bigger, your outermost electrons are just farther from the nucleus, which means they're not held as tightly. It's easier to pull them off. And that's your general trend that you see. So ionization energy, general trend, increases up to the right, I think is the normal way I like to think about that. And this is a quick visual image. And so here is, and it looks like it resets each row because it kind of does. So within a row on the periodic table, it increases up to the right. And this is basically as we move to the right through a row, we see our ionization energy increasing. And then as we go down a column, like they're a little bit lower, go down another column, they're going to be a little bit lower, and so on. And I do want to highlight there's kind of some little blips in the trends, right? And so there are some situations where we see some deviations from the normal trend, and I do want to talk about those. Because if we understand things with electron configurations that we talked about before, we can actually make sense of the trends that we see here and the exceptions to those trends. So what I mean by that, here we see this is a zoomed in look at the second row and third row of the periodic table and what their ionization energies are. So as we move to the right, so increasing atomic number, moving to the right on the periodic table, generally our ionization energy increases. But there's two spots where it stops and actually decreases a little bit. One is between beryllium and boron, one is between nitrogen and oxygen. And if we think about why does that happen, I'm going to jump back out to a periodic table again. Between beryllium and boron, we're going from beryllium, if we go to take an electron off, beryllium is s orbital right here is full of electrons. And remember one of the things we said about why like chromium and copper were electron configuration exceptions before? Full and half full orbital shells are extra stable. So breaking up a full 2s orbital actually takes a little bit of extra energy than what we would normally expect. The counterpoint of that, if we look at boron, if boron loses one electron, it only has a full s orbital, which actually means that's probably a slightly more stable configuration than normal. So it's actually easier to ionize boron than normal because it ends up with a full s shell, and it's harder to ionize beryllium than normal because we have to break up that full s shell. And that's why we see this kind of blip in our normal trend. Beryllium actually has the higher ionization energy. And then between nitrogen and oxygen, we see almost the same thing. The only difference here is now we're in the p block. So between nitrogen and oxygen, nitrogen, it's not that it has a full shell, but it has a half full shell, right? We think about our p orbitals. I think I still have some sketch over here. Like if we have 3 p orbitals, right? 4 electrons in them is what oxygen would look like. It would just be 2p instead of 6 here. And so 4 electrons, if I take one away, it's now half full. Half full is slightly more stable than normal. So it's actually easier to take 1 electron off of oxygen than you might normally expect given the general pattern of things. Nitrogen, on the other hand, already has a half full shell. So nitrogen's already pretty stable because of that. And it's actually harder to take that 1 electron off of nitrogen than we would normally expect otherwise. And the end result of all of that is when we look at our trend that we were just mentioning. If I go back to my PowerPoint here, the trend that we see is that nitrogen's ionization energy ends up slightly above that of oxygen's. We actually see that in other rows in the periodic table as well. So between magnesium and aluminum, that's the same spot in the periodic table, right? Magnesium to aluminum is the same as beryllium to boron. So anytime we go from group 2 and are skipping over here to what's really like group, what we call 13 on most periodic tables, like there's always going to be that slight deviation in the ionization energy. Usually group 2 is always a higher ionization energy than the group 13 elements in the same column. And we also see it between groups 15 and 16. That's basically between the 2 columns with nitrogen and oxygen in them. And so here we see like nitrogen again and everything below it, half full p shells, oxygen and everything below it. If it loses an electron, it will have a half full p shell. So the end result is a lot of times these elements here in group 15 either have about the same or even slightly higher ionization energies than what we see out of group 16. It's kind of so that's where we get our deviations to the normal trends of things. But again, if we understand electron configurations and the fact that these half-full sets of orbitals are kind of extra stable, or that full orbital sets are extra stable, that gives us kind of some reasoning now to be able to understand some of these exceptions to our ionization energy trends, so that hopefully you don't just feel like you have to memorize which elements have exceptions. You can kind of actually make sense of which ones have those exceptions. And that's really kind of the goal of a lot of these things with periodic trends. We want to understand the trends, but also understand some of the exceptions if we see them. All right, back to ionization energies, some other things that we can talk about with them. And again, this is kind of the summary of the exceptions that I've just been talking about, so I'm not going to spend too much detail rereading you this slide. If you want to pause it here so you can have kind of a written description of a lot of what I've been saying for the last couple minutes, then you can feel free to pause it here and kind of write some of those things down a little bit. But I'm going to go ahead and move into the last little bit with ionization energies I want to talk about, which is doing what we call multiple ionization energies. So it's possible for you to actually ionize a particular atom more than once, which basically just means instead of ending at like a +1 charge, you want to end it at like a +2 or a +3 or so on. So that's really what I mean when I say these multiple ionization energies. Now, if you take a second electron off, we call that the second ionization energy. The third electron you take off will be the third ionization energy, and so on. And the trend is that each additional ionization energy is always higher in energy than the one before it. Always. Even, I'm just, again, kind of bounce out to a periodic table here. Even if we go from a group 2 element to a group 1 element, beryllium, since it's in group 2, we know group 2 elements like to be +2. Once we take one electron off, if it loses one more, it's at that +2 charge it normally likes, but it's actually still harder to pull that second electron off than it was to pull off the first one. The reason for that is once you take one electron off of your starting atom, it's now positively charged overall, and to take an electron off of an already positively charged particle is always going to be harder than taking an electron off of a neutral compound, or sorry, a neutral atom. And so that's kind of what we see out of that pattern. Each successive ionization energy for any one particular element will always get bigger because you're basically having a bigger and bigger positive charge that you're trying to pull that electron away from, and it's just harder and harder to do. All right. Now, one other aspect of these multiple ionization energies. So not only will each additional ionization energy get bigger, but the other feature is that we're going to see at some point with those ionization energies, they're going to kind of steadily increase, and then all of a sudden we're going to see this enormous increase in ionization energy. And we're always going to see that basically coincide with when your atom doesn't have any more valence electrons to lose, and you're trying to take off a core electron. So those two terms that we talked about in the previous lecture, like core electrons versus valence electrons, valence ones being your outermost, those valence electrons, when you take them off, are much easier to take off because they're the outermost ones. And your core ones, because they're much closer typically to the nucleus and held much more tightly, they're really hard to take off. So ionization energies for core electrons are huge because it takes a lot of energy to pull off those core electrons. They're held very tightly. Whereas valence electrons, a lot easier to pull off. So to kind of demonstrate that, so this is a chart that has basically successive ionization energies for a lot of different elements, again, in the third row of the periodic table. And what I want to highlight is as you go down a column, note, and you'll see it with the kind of the stair-step region here, like as you go down, you're going to see there's only one spot where there's like a huge increase compared to kind of everything else. For sodium, we see this goes from like 400, just to about 500 kilojoules per mole for an ionization energy, immediately to 4,500, which if you think like in a percent increase, like it's, or just like a kind of a, by what factor did it go up? It went up by almost a factor of 10. That's a huge increase, whereas like going from 4,500 to 6,900, even though it went up by like 2,400 or so, it didn't even go up by a factor of 2. Here it went up by a factor of 10. That's an enormous change in comparison. So this first to second ionization energy jump for sodium, the reason this really big spike happens here is because sodium only has one valence electron. If you look at the periodic table, it's in group 1. So the second electron you pull off of sodium is a core electron, so we get the big jump. If we look at magnesium, first ionization energy 738, second one about doubles. The next one goes up by a factor of about 5, right? So it goes from 1,400 to 7,700. And the next one doesn't even double again. And so the big jump is right here. And that's because magnesium, again, has 2 valence electrons. It's in group 2. And we can kind of follow this all the way throughout the periodic table. If we go to things later on, like sulfur, for instance. Sulfur, here we see its ionization energy kind of steadily increasing by about like 1,000 kilojoules per mole. It's not even doubling for any of these. And then all of a sudden it goes from like 8,400 to 27,000. So it went from like not even doubling, going up by maybe 50% or so each time. And then it goes up by a factor of 3, like 300%. And so that's the big change out of all of these. That's because the 7th ionization energy way down here, sulfur has 6 valence electrons. So that 7th one you pull off is a core electron. It's just much harder to do. All right. Now, one other trend, again, before we get to examples, one other trend that's really similar to ionization energy is something called electron affinity. You will sometimes see it abbreviated like EA on some of the abbreviations for things in this chapter and probably the next a little bit as well. And electron affinity, it's really similar. Like ionization energy is the energy it took to take an electron off. Electron affinity is usually the energy change when an electron is added to something in the gas phase instead. So instead of taking an electron off, getting a cation, you're adding an electron and getting an anion instead. Usually this energy is going to be negative because when this happens, like if you add an electron to a lot of different elements, they actually get, at least for the nonmetals, they get more stable. Like they actually typically like to be negatively charged for a lot of nonmetals. And so it's actually an energy release when this occurs. And so you'll see negative values for a lot of electron affinities. And so you do see, like I'm going to show here, like the numbers, everything's kind of negative, like going up on these trends. In terms of what is the general trend for electron affinity, it's pretty much the same as ionization energy if you think about it from kind of a magnitude standpoint. So if you don't worry about the negative, the fact that it is a negative value typically, just thinking about it in terms of like what's the overall energy change, it's bigger energy changes as you go up to the right on the periodic table. So if I, again, kind of zoom back out to a periodic table, the biggest electron affinities are near the top right of the periodic table because these are the elements that want to be negatively charged. Right? Bottom left of the periodic table has very, very either small or even positive electron affinities because they really do not want electrons. Right? Metals usually make cations. They usually lose electrons instead. And for electron affinity, it's not quite as straightforward on exceptions and things like that as ionization energy is. So a lot of times we won't talk about electron affinity trends, or at least exceptions to trends, nearly as often. Usually ionization energy ends up the bigger focus of those two, but I did want to introduce the general term because you'll probably see it in the next chapter. All right, one last trend, and then like I said, I'll do some wrap-up examples for us. And so this last one, electronegativity. If we want to know what electronegativity is, it's the ability of an atom to pull electrons towards itself in a chemical bond. So how that generally works. If we want to think about kind of like what's going on, if two atoms are bound to one another through what's called a covalent bond in particular, your electrons are usually shared in that type of bond, but they're not necessarily going to be shared evenly. One atom's usually going to want the electrons a little bit more, and again, it goes back to effective nuclear charge. The higher the effective nuclear charge of an atom, the better it's going to be at pulling electrons in a bond towards itself. And if you remember back, effective nuclear charge's trend was that it got bigger as you went up and to the right. So what happens for electronegativity? It's also going to increase as we go up and to the right. So higher effective nuclear charge on atoms, higher electronegativity for those atoms as well. And something we'll talk a lot more about as we get into chapters 8 and 9, when we talk more about covalent bonding in particular, and some different trends and properties that will come with that. You'll actually see that we have numerical electronegativity values from something called a Pauling scale that we can assign to each element. And we see that the most electronegative element is fluorine. And then as we move away from fluorine, those numbers get lower. But again, up to the right, as we go up to the right in the periodic table, electronegativity, that's where it gets its highest. Kind of ignore the fact that transition metals are a little weird in here. If you're really interested or intrigued by that stuff, again, I'll kind of throw a pitch for myself for inorganic chemistry that I teach for a senior level class where we will spend plenty of time in a course like that kind of getting to talk about those things. But for general chemistry, we care about the elements that are the most common, which are mainly going to be our nonmetals up here in our group 1 and 2 metals. And for those, our general trends pretty much all hold up. All right, so to wrap up with things kind of here today, we've introduced kind of a number of kind of these periodic trends. So just some last comparisons to kind of make sure we're all on the same page for what to expect for kind of questions for kind of things like this, and making sure kind of we're hopefully making sense of the general concepts. Here I have a few questions, like question number 2, each of the Pauling pairs, identify which element has the higher effective nuclear charge. So the first one, we have silicon or sulfur. Well, if we're thinking about which of these should have the higher effective nuclear charge, let's look at our periodic table. So if I pull our periodic table over here, we're comparing sulfur and silicon. We were looking at Z effective. We said Z effective gets bigger as we go up to the right. Well, sulfur is farther to the right than silicon, so sulfur should have the higher effective nuclear charge, right? So that should be our answer. If we compare oxygen and sulfur, these are now in the same column. Again, we said it increases up to the right. Oxygen is higher up out of those two, so oxygen should be the one that has the higher effective nuclear charge if we're comparing oxygen and sulfur. Right? If we look at sizes again, reviewing atomic size and ion size. So for, again, each of the pairs, identify which one has the bigger size or bigger radius. So if we compare sodium and fluorine, this is one we actually talked about earlier. Right? Fluorine is over here. Here is sodium. The general trend for atomic size, and one way now that we've kind of talked about all of our trends, if you've paid attention, every trend we've talked about increases up to the right. The only one that doesn't is atomic size. It's the exact opposite. It increases down and to the left. So if we go down and to the left, that's how we get from fluorine to sodium. So sodium should be the bigger atom of those two. If we compare arsenic and phosphorus, so here's phosphorus, here's arsenic. Arsenic is farther down. We said atoms get bigger as they go down, so arsenic should be the bigger of that pair. If we compare aluminum and phosphorus, now we're back to things in the same row. Again, to the left and down is bigger, so aluminum is farther left. Aluminum should be the bigger of those two elements. And now if we look at ion effects, well, if we have sodium plus versus normal sodium, again, as we get to positive charges, we had to remove electrons, which means fewer repulsions, which means things are actually going to shrink and get smaller. So the neutral atom is always going to be bigger than the cation. And if we think about anion trends, so if we want to compare bromine and bromide, it's the opposite trend, right? Bromide, as we add an electron that's extra repulsions, that means our electrons have to spread out more, so our ion gets bigger. If we compare Na plus and F minus, now we're in a situation where we want to make sure these things can really even be compared. F minus, we take fluorine and add one electron, it's like neon. Sodium plus, if we take an electron off of sodium, it's also like neon. So they are isoelectronic, so we should be able to compare their sizes. Sodium has 2 more protons than fluorine does. That's why it has the positive charge instead of a negative charge. So sodium, because it has the extra 2 protons, is able to pull the outer electrons in tighter, which is going to make it smaller. So the one that's bigger should be the one that's more negatively charged usually in these comparisons. So fluoride should be the bigger one of that pair. All right, for ionization energies. And really, like electron affinity and electronegativity would follow pretty much the same trend here as well. For each of these following pairs, we want to identify which element will have the higher first ionization energy. And we have silicon and sulfur again as our first one, similar to what we had above. Well, if we compare silicon and sulfur, sulfur is farther to the right than what the silicon is. And this follows the same trend as effective nuclear charge. It increases up to the right. So sulfur should have the higher ionization energy. If we compare carbon and silicon, carbon is higher up on the periodic table than silicon is, so carbon should have the higher ionization energy as a result. Its electrons are closer to a nucleus, they should be harder to pull off. And then we have boron and beryllium. And so remember, this ionization energy trends aren't always super straightforward. I think most of them are going to follow the general trend, but occasionally we have to be on the lookout whenever we're going from group 2 to group 13, because remember we said group 2, you have a full S shell. They're going to have higher than normal ionization energies because they don't want to break up that full s orbital. Whereas for boron, boron just has a single electron in a p orbital that if it loses it, now it only has a full s orbital, which it's perfectly happy with doing. And so it's easier to ionize boron than you'd normally expect, harder to ionize beryllium than you normally would expect. So this is where we see our exception. And beryllium actually does have that higher ionization energy. And so that does pop up from time to time. It's not really common, but probably the biggest place to look out for, group 2 going to group 13, our ionization energy actually goes down between those two groups. Otherwise, as we go across, it's usually going up. Between groups 15 and 16, so like nitrogen's column and oxygen's column, we see a little bit of that between those two columns as well. Outside of that, any other comparisons, it'll always be increasing up to the right. And to kind of give more to that, like if you compared carbon and oxygen, like oxygen's farther right, it has the higher ionization energy. So the only time that up to the right trend doesn't necessarily work, or really just doesn't work, is between groups 2 and what we often call 13 with boron, and between groups 15, which is nitrogen's column, and oxygen's column, group 16. Right. One last question, then we'll wrap up. I think it's been playing long already. So the last one here, which ionization energy of phosphorus will see a dramatic increase from the previous ionization energy? So this kind of deals with the multiple ionization energies we were talking about before. And we said that the big increase in ionization energy happens when we try to take off a core electron instead of a valence electron. So we're looking at phosphorus. So here's phosphorus in the periodic table. If we want to think about how many valence electrons phosphorus has, 1, 2, 3, 4, 5 for the things in its column. So phosphorus has 5 valence electrons. So its 6th ionization energy should be where we see the huge spike in those ionization energies, because that's when we would start to be removing a core electron. So we'd expect basically the 6th ionization energy, 6th ionization energy to be our spot where we see that big change. All right, so I think that's pretty much all I have for this time. We've covered all kind of the slide materials here, and really that's kind of all of Chapter 7 we'll really focus on. There is more to it, I think, like I mentioned before, that talks about something called descriptive chemistry and kind of some general chemical and physical property trends for the different columns of elements in the periodic table. We tend not to focus too much on it. It's mostly just memorization. There are some neat or useful things you can get from reading that if you're interested, but especially with kind of our slightly condensed schedule here this semester, and even during normal semesters when we're face-to-face, even then we usually don't talk too much about those topics. So we're not going to spend really a lot of time focusing on those. Like for my classes, I'm not really going to test on those. If Mr. Herbert or if Dr. Herbert or Mr. Kruger wants to supplement those maybe a little bit more, they might. But I think most of us usually don't spend too much time talking about those descriptive chemistry trends. So for my class, this will be probably the end of the content for the next exam that's coming up next week. I will likely have slides posted for Chapter 8 before we take our test. But that Chapter 8 material on like Lewis structures and things like that won't be on my exam. For Dr. Herbert's sections or Mr. Kruger's or anyone else that's using this, you might want to check just with your individual professors. Everyone's kind of exact cutoff spot for some of the exam topics may vary just a little bit. But that's all I have for this time. Hope everyone's staying safe out there still, and we'll see you at the next one.